All right. Hi, everybody. My name is Amit, and I'm a software developer. Over the past 3 years, I worked in an IoT platform company, mostly in the embedded firmware department. I got to work with the Bluetooth protocol, learn and perform a proof of concept of Bluetooth 5. During the process, I found useful information, and I've decided to gather those pieces of information from the BLE platform companies, reading and leaving questions in the forums, protocol specifications, and a little bit of hands-on into this brief lecture. Actually, when I decided to gather all of my summaries into this lecture, I got a little bit disappointed as now there are many more articles and official information on the subject. But I still wanted to make here what I think is the friendly, quick, full guide, which includes everything that I needed and looked for. So I hope you'll find it useful as well. In addition, I'll put some extra links of great resources at the end of this lecture.
So what are we going to have today in this lecture? We'll detail the differences between the BLE 4.2 and the Bluetooth 5. So Bluetooth 4 and above are the protocol's versions well known as the BLE Bluetooth Low Energy. Bluetooth 4.2 is the most popular choice in the IoT market. This version introduces features for the IoT world and is natively supported in most of the mobile operation systems. The Bluetooth 5 protocol is backwards compatible with BLE 4.2, but you must make sure you allow and handle it as well when it comes to the app layer. So the differences are all additions to the BLE 4.2. We'll explain the improvements. How are they achieved by explaining important terms, concepts, and some pros tips if we'll have the time. And once we understand how it works, we can also understand the trade-offs and what to choose and what would be good for you to get right on track with your next project. So without further ado, the enhancements are the LE2M5, also known around the web as double the speed feature, the coded PHY, also known as 4 times the range around the web, and advertising extension, which would I like to call it the beacon's delight. All right, so let's get started by talking about the first two PHYs, the double the speed and 4 times the range. Well, a common mistake regarding the Bluetooth 5 is that you can get faster data rate and longer range. Don't get me wrong, Bluetooth 5 is a significant achievement, but you don't get the best of both of the worlds at the same time. Bluetooth 5 allows you to go faster or further, but not both, by choosing between additional 2 new PHY options, the 2M PHY and the coded PHY.
In order to talk about PHY, we first need to understand what PHY is. So let's say I have a smartwatch, and on my smartphone, I have an app with a super convenient UI where I can easily manage my watch settings, like changing the color of my screen. Then it sends the settings over BLE to the watch. Both the smartphone and the watch have a BLE stack, so they could communicate over BLE. The controller is the lowest level on the stack and the only module with hard real-time requirements in contact with the physical layer. So it talks directly with the BLE hardware. Within the controller lays the PHY. PHY, the physical, hence PHY, is the part that actually contains the physical hardware for analog communications. It's capable of modulating and demodulating analog signals and transforming them into digital symbols. So it's the middleman between the analog world and the digital world. PHY is the layer that really passes over the air the data which will eventually be interpreted on the other side. In our small example, just to get the general rough idea, the app layer on the mobile phone will receive the user settings like screen color choice blue and pass it through the lower host layer until the PHY will pass the data over the air by signals to the PHY of the smartwatch. The received data on the watch will go up the stream through some checks, modifications, etc., and will be received on the app layer of the watch, where the model that is in charge of the screen can set it to the requested color.
So let's start by talking about the 1M PHY. This is one of our options that we have now in the Bluetooth 5. This PHY was introduced already in Bluetooth 4, and since then until Bluetooth 5 was the most favorite and only PHY option in the BLE. LE stands for low energy, as in BLE, and 1M refers to how many beats are being transferred. So 1M PHY have a symbol rate of 1 megasymbols per second and data rate of 1 megabits per second, meaning in general, when the hardware sends data over the BLE, every second there are 1 mega modulated signals transferred. Each signal represents 1 beat. I'll also mention that it uses modulation method called binary Gaussian frequency shift keying. For whoever is interested in more information about this modulation scheme, I'll add a great explanation link at the end, but this is not in our scope for today. So 1M PHY continues to be available to use in the Bluetooth 5, and its support is actually mandatory. So this is in order, of course, to preserve the backwards compatibility. So devices that implement now the Bluetooth 5 can still communicate with devices that implementing the Bluetooth 4.2. The second new PHY option, this is the 2M PHY. This one operates at 2 megasymbol per second and thus enable higher data rates. Here as well, the modulation is binary Gaussian frequency shift keying. But while the LE1N uses a frequency deviation of at least 185 kilohertz, the 2M PHY uses a frequency deviation of at least 370 kilohertz. The signals are running twice as fast, so in the same amount of time, you get twice the data. Or another way to say it is 2 beats represented in the times it used to be enough for 1 beat. It doubles the single rate that the LE1M PHY uses, but not necessarily the entire operation. When talking about network speed, we should distinguish between throughput and data rate. Different data speeds measurements, both measured in beats per second. Throughput is the effective overall amount of data sent during a time period that a flow can send or receive. It includes all the host and protocol handling overhead, maintenance, and other traffic on the link, etc. So this is what I call from door to door. The data rate, well, this is the rate that the beats are transmitted from source to destination devices. So if the first one was from door to door, this one would be like, how long does the bus drive take? As you understand by the example, the throughput is usually measured in a higher level of the network than data rate. So usually the throughput would be smaller than the beat/data rate. For wireless connectivity, there is some transmission cost for robust link maintenance and packet processing, which does help overall efficiency, but still takes its time. So eventually, while the bit rate is double the speed, the total throughput of the 2M PHY is actually not double, but around 1.7 times greater than the BLE 4.2. When do I want to use it? Use cases demanding low power communication, which supports high data rates, like firmware upgrades over the air, audio streaming, medical and fitness devices, buffered sensors, sensors that keep sampling and accumulate data, and then you need to read the entire data at once, and etc. LE-coded PHY, also known as long-range feature. This feature supports 1 megasymbol per second of symbol rate, just like the 1M PHY, but it uses error collection coding. What does it mean? As further the distance between the transmitter and the receiver, more chances for an error to occur. This intuitively makes sense, like to throw a ball or yell towards someone who's far away. We wouldn't like to use more energy to yell because BLE literally stands for Bluetooth Low Energy. Its goal is to function with low power consumption and have the longest battery life as possible. So if we don't want to use more energy to yell, then maybe we can increase the listener's sensitivity. The listener can't hear everything, but maybe it can still understand, thanks to the parts that it can hear. In communication systems, errors are dealt with two common strategies. The first is error detection, and the second is error correction. Error detection already existed in the BLE4. It uses CLC. So I'm not going to get into what CLC is right now, but if you're interested, of course, you can look it up online. But I'll just explain that in case of a failure, the receiver does not acknowledge, and due to the lack of the acknowledgement, the data will be retransmitted, what takes its, of course, time, battery life, more power, etc. The error correction not used to exist until the Bluetooth 5. In case a failure has been detected, we can still interpret the data. How does it do it? Bluetooth 5 uses coding, a set of rules to convert information. Coding theory is a science field studying data compression, cryptographic coding, error control, and more for data transmission and storage. Hence, coded PHY, like using coded. The LA coded PHY has forward error correction by using convolutional code in order to correct errors. More about this in the links that I will add at the end. But for now, what we want to understand is that each beat will be coded into more beats. Let's say I have the beat 1. This one will now be represented by 1 and 0. If I want to send the beat 1, it will first be coded into beats 1 and 0, and then transmit those beats. That way, even if an error occurs in few of the transmitted beats, the receiver gets like a partial data, and then it has the better probability to recover the maltransmission. What if we want to get even further? Then why coding into only 2 beats? We can also represent each beat by 8 other beats and get even better chances for the receiver to understand. And that way we can get even further. So each beat from the previous stage can also be now mapped into 4 beats. So we had our 1 beat and we represent it by sending 2 beats, which is the 1 and the 0, but now they'll be mapped the 1 into the 1, 1, 0, 0, and the 0 will be mapped into 0, 0, 1, 1, and eventually get 8 beats transferring by 8 modulated signal per each beat that we originally wanted to send. In Bluetooth 5, they give you the 2 options. They named them S2 and S8. S2 is 1 beat represented by the 2 modulated symbols as we've seen in the previous slide, and the data rate is 500 kilobits per second. S8 option is 1 beat represented by the 8 modulated symbols, and the data rate is 125 kilobits per second. You do get further range thanks to the less chances of path loss, losing data on the way, without using more output power for your amplifier. So talking some numbers, it improves the receiver sensitivity from -70 dBm, which is the minimum required by the BLE protocol, or, well, -97 dBm, which is actually the effective, up to the -103 dBm. If it means nothing to you, take it as it's better, without additional power consumption. But do you really get the lower power consumption in your application now? Not necessarily. Since the data rate is now lower, the connection could be held for longer. Connection demands a lot of power when it comes to the IoT devices, so you might end up waiting for the entire data to be received and wasting precious battery life. Make sure to create really good benchmarks testing your use cases. When do I want to use it? The reason the coded PHY is such a big deal is because it promotes BLE network from being a wireless personal area network to a home area network. This family has much more options in the real life and the IoT world, where the smart home sector is a leading example. When considering the S=2 option or the S=8 option of the coded PHY, note that due to the structure of the data packets transferred, most of the time you want to use the S8 option. There is an overhead anyway, and you might as well enjoy the benefit of the range. Only if you're transmitting more than tens of bytes, well, then you better use the S2 mode. Few important notes about the PHYs. PHY on Bluetooth 5 can be changed on runtime, meaning you can change 2M or coded PHYs according to the use cases in the application levels, as long as the host exposed the feature, of course. Why not all devices declaring support in Bluetooth 5 will work as mentioned? Implementation is optional for the 2M, the coded PHYs. Devices can just have one of them or neither and still declare a Bluetooth 5 implementation. Which leads me to a word about range test. When I was working with the Bluetooth 5, there was only like one in the market which supported Bluetooth 5. And it as well was brand new. Therefore, most of the POC was conducted with 2 Bluetooth evaluation boards. And only later, we could replace the central device with the smartphone. So whoever is interested in conducting range tests and would like to consult is very much welcome. I do have some tips, and I could guide you on how to check whether the device really supports the Bluetooth 5 or not, and if it really supports the features that you're looking for, like the long-range one. This also leads me to the comment below of the table. Testing the range depends on so many variables that you should test it in an environment as similar as your use case, taking into consideration obstacles on the path and their materials, angle of the antenna, noise on the channels, etc. On the Bluetooth website, they have an easy range calculator which you can use for your estimations. I find it pretty pessimistic because most of the results that either we got or you could find online are better than the ones that you get by the calculator. So what did we have so far? We talked about how we can now choose our PHY level and about the new additional PHY options with a 2M, which is faster, and the coded, which is further. And we love to talk about the advertising extension. There is not yet a lot of information on the advertising many improvements around the web. I guess it hasn't been used much in the market yet. I would look into forums or the official protocol specification when you have questions regarding the changes in the advertising system. Whoever is familiar with the 3 different sets of advertising that can be issued, added in BLE 4.2, I think, it is still supported in the BLE 5. And I believe that if you use this feature, then questions might arise regarding to its coexistence with the new Bluetooth 5 features. So let's go over few of those main Bluetooth 5 features regarding the advertising. First of all, advertising messages, the DPU size grew from 31 bytes to 254 bytes. Not only that, but now you can chain advertising payloads and get even more per advertising. As you can see in the upper right illustration, each payload packet also contains a pointer to the next payload packet. The pointer has information regarding the following channel that it will be advertised on. As you might know, the golden rule says that primary advertising channels 37, 38, and 39 carrying less data and secondary channels 0 to 36 doing most of the heavy lifting. That's why we're going to go to our next feature, which is the payloads on a secondary channel. Bottom left illustration. In the BLE 4.2, the advertising was on the primary channels and the data sent during connection on the secondary. Since the advertising payload is so large now, a change was needed in the channel systems as well. In Bluetooth 5, on the primary channels, you will find only the main header and a pointer that leads you to the first advertising data payload. That way, only the header is transmitting on the 3 advertising channels, and the actual advertisement is transmitted only once in any of the 0 until 39 BLE channels. With advertising data using all available channels and only small headers using the primary channels, there will be less traffic on those channels. Moreover, thanks to transmitting 3 times, one on each primary channel, only the small headers, and then just once the huge payload, the duty cycle not only isn't larger, but actually has been reduced. When do I want to use it? This is mandatory to use the extended PDU in order to use the LE coded PHY. And there's an exclamation mark over there because you can also find it out in the hard way. These are huge changes in the advertising mechanism. Establishing and maintaining connections consumes so much of resources, mainly battery life, that now you can transfer so much data without even connecting, just by broadcasting. This is especially great for beacons who are unconnectable. And that's it. Thank you for listening. I believe that you have now all the needed information to start with your project, and I really hope that you will find it useful. These are the links I promised. Feel free to contact me if you have any questions, and good luck.